Welcome back, everyone. We're in chapter 14 on acids and bases. An acid and base is extremely common in chemistry. As things react together, a lot of times what's actually happening is you're having a transfer of a proton. Often you'll have transfers of electrons, those are called oxidation reactions, and other times you're going to have a reaction where a proton is donated or received. Those are called acids and bases. These are not types of reactions like combination or decomposition. These are actually what's happening, what's being transferred in that chemical reaction. So this is a type of reactant, which is an acid and a base. And you're going to see that many of the compounds that we already have seen are actually acids or bases, and they can act sometimes as an acid or a base depending on the situation. So since this is a little complicated, we have to look at it in kind of steps. And so we're, first of all, just going to identify what acids and bases are, and we're going to have a couple different definitions. This section is dealing with a definition proposed in the 1920s by two different scientists who were working at the same time and independently. So they were not sharing the results, and they both independently came up with this idea. So they're kind of famous together as the idea of what is an acid and what is a base. Long before this, even the alchemists would know that certain compounds are sour. Okay, sour. We looked at Arrhenius bases. Okay, those Arrhenius is 18th century. So even before then, you had acids that were sour, like lemon juice. You had bases that were slippery or bitter, like lye. And so there was a concept of this idea of acids and bases neutralizing each other. People knew when they had an upset stomach that they would eat certain plants to kind of make them feel better. So they were playing with the ideas of acids and bases. But it wasn't until the 20th century that you kind of broke it down, analyzed it enough to know what was actually going on. So this is our second definition, Bronsted-Lowry acid and base. Before I get any further, I have to show you a molecule called a hydronium. It's actually an ion. If, let's say, water breaks apart, which it does, water can break apart, and if it breaks apart, one of these arms breaking, it's going to break apart into a hydroxide, that's OH, which we know is a -1 ion, and then the H is going to be broken apart, and that's going to be a proton. Do you remember that this oxygen is bigger than the hydrogen, and it's holding on to the electron pair that's sharing closer to the oxygen? So if this arm is torn off for any reason, the electrons stay with the oxygen, and that electron makes the OH negative. That's what hydroxide is, -1. The hydroxide, or the hydrogen, has lost its electron, so now it becomes a proton. If this proton could react with a water molecule, which it very often does, you're going to get something called a hydronium ion. And later we're going to see that that's an acid. If you know anything about pH, the pH of something, the pH is essentially measurement of an acid. And the H in pH is the hydronium. So how many hydroniums do you have in a solution? Well, what you're doing is measuring its pH. You're measuring its acidity level. So first thing you need to know is that a proton can react with a water molecule to form an ion called H3O, which is called hydronium. All right, so here is a basic Bronsted-Lowry idea of an acid. An acid is anything that can donate a proton. And remember, a proton is a hydrogen ion, so a hydrogen that's lost an electron. So look here. Hydrogen's the little guy, chlorine's the big guy. It's sharing an electron pair, but unequally. The chlorine is pulling it harder than the hydrogen is. So the electron pair is actually closer to the chlorine, and if it breaks apart, the hydrogen will go away as a hydrogen proton, okay, as a H+. So that's one proton is a hydrogen ion. The Cl is going to keep that electron and become a chloride ion. Okay, so if this ever breaks apart, it's going to break apart unequally, and the electron gets, she gets to keep the house. All right, so this proton is then going to react with water in this example. The water is receiving the proton, so the water is the base. So an acid donates a proton, so the HCl, the hydrochloric acid, would be the acid or the donor of the proton. This example, the water is receiving the proton, so it's becoming the base. So you have two reactants. In this example, you have an acid and a base reacting together. And when it reacts, the proton exchanges. What used to be the base, the water, now has 3 hydrogens, and it is now an acid, because if it were to give away one of these hydrogens, it would be acting as a proton donor, and so can be considered an acid. Once the HCl has given away one of its one and only hydrogen, it now doesn't have the hydrogen. It could receive one back, and since it could receive one back, it's now considered a base. So think of it as a ball game. If you have a proton to donate, you are the acid. If you receive the proton, you are the base. You're catching the ball. But once you have caught the ball, you now have the proton to give, so you're no longer a base. You're now the acid, and the one who threw it to you in the first place doesn't have it, so it's now the base. So think of it kind of like a game of catch. We're going to see this again when we see oxidation-reduction reactions, where it's not the proton that's donated, but the electron that's donated, and it also acts like a ball game, where one is giving the electron to the other, and then back and forth. In this case, in acids and bases, it's the proton that's being donated. Here's another example. You have ammonia and water. Okay, so let's look and see what happened. Who gets more hydrogens at the end? Ammonia has 3 hydrogens to start with. Water has 2. Both of them have one to give, so I'm not sure which one's the acid. Let's find out what happens. Here I have ammonium has 4 at the end, and hydrogen has 1, or the hydroxide has 1. So that looks like water over here has lost one of its hydrogens. It's being donated to the ammonia, and at the end of the reaction, the ammonia now is called ammonium, NH4, positive 1. Remember, it's the only polyatomic ion that's positive. And then whatever's left over of the water is no longer water, it's a hydroxide ion. So essentially one of the H's fell off of the water and is put onto the ammonia, and then it becomes ammonium. Okay, so which one's the acid? Which one gave away hydrogen? The water is acting as the acid here. Okay, remember, water was the base in the last example. So water, since it can receive or give away protons, can act either as an acid or a base. And we'll see that there's a name for that. So here we have the water is the acid because it's donating the hydrogen. Base here is the ammonia because it's receiving the hydrogen. Now on this side, it's already received it, so it now has the ball. It has the hydrogen. It's now considered an acid. Okay, by itself it's an acid because it could give away a proton. The water now, once it's lost one of its hydrogens, is now hydroxide, and hydroxide's a beautiful base because it could now catch a proton. So essentially it's a ball game back and forth of losing, donating, and receiving protons. So I've already mentioned this before. A lot of people find this complicated, but you basically have 2 things. You have someone with the ball, that's the acid, and you have someone without the ball, that's the base. Okay? So let's imagine that I have the ball in my glove. I'm the acid because I have a proton to donate. I throw the ball to you. Now I don't have the ball anymore, so I do not have the hydrogen ion to donate, so I'm no longer an acid. I can receive the ball from you if you were to throw it back, so in that case I'm a base. You want to think of whoever has the ball as the acid, and whoever has lost the ball as the base. Okay, now this idea is called conjugate acid and base. Now I want you to only look at you, don't look at me. I've got the ball, you don't have the ball. I throw the ball to you, you accept it. That makes you a base. You're getting it thrown to you. As soon as you get the proton, you are no longer a base because you already have the new proton. You then have the ball, so you are an acid. Okay? You are an acid if you have the ball, and you are a base if you don't have the ball. But it's still you. Okay? A conjugate acid and a base pair is one molecule that can act as an acid when it has a hydrogen and act as a base when it doesn't have a hydrogen. Okay? So going back to one of the examples, here's an acid because it has a hydrogen. Okay? I'm dumb. In this case, the water is receiving it, so this is the base, and then it got an extra hydrogen, now it's an acid. This is called a conjugate base-acid pair, or acid-base pair. This oxygen and hydrogen, when it has a hydrogen to give, it's an acid. That's here. When it has 3, when it only has 2, it's a base. Okay, because it's essentially one or the other. It's an acid if it has the hydrogen to give. It's a base if it's receiving it. Here's another example. Okay, the acid was the water. The water gives away one of its hydrogens and then becomes hydroxide. So if it has one to give, this is an acid. If it doesn't have one to give, it's a base. These two guys are acid-base conjugate pairs. Conjugate meaning it's the same guy, one with the ball, one without the ball. Okay, so the idea of conjugate acid-base pair is that you've got the same guy, one with the hydrogen and one without. Look here as an example. I've got hydrofluoric acid. So I've got the hydrogen to give and fluoride. If I give away the hydrogen to water, okay, if I give it to the water is receiving it, so the water's the base. The acid has it to give, so the hydrofluoric acid is the acid. What's left over when I give the ball away? What's left over is the fluoride ion. So this is the conjugate acid. This is the conjugate base. Okay? Here's the base. It receives the hydrogen. It now becomes an acid because it has something to throw away. It has one to give. So these two guys, which are the same thing, it's H2O and H3O plus, these are conjugate acid, here's the acid, base pair. So in an acid-base reaction, you have two conjugate acid-base pairs. The original acid, and then whatever's left over when it throws the ball. The original base, and whatever it becomes when it grabs the ball. Okay, that's an acid-base pair. And what's happening is it's a proton transfer. Okay, the conjugate acid-base pair, okay, is a transfer of a proton. So here is an acid. Okay, here's an acid. It gives one of its away to the ammonia. It becomes NH4. So here's the base, and then this becomes the acid. Okay, here is the acid, but once I've given away the proton, I no longer have it. This is what's left over. That's the base. Hydroxide is the base. Water, in this case, is the acid. Okay, ammonia is the base, and then over here, the ammonium is now the acid. Okay, so what you're going to see is that there's a backwardness. If you have a very strong acid and it gives away its hydrogen, what's left over is a very weak base. If you have a very strong base and it receives a proton from the acid, you'll end up with a very weak acid. Okay, so these are actually backwards of each other. One is strong and one is weak, and we talked about strength, and I'll talk about it again. All right. Obviously, you'll need to work on this and ask me questions. I'll see you in class.